Good morning, students. Hope all of you are doing good. You're following the videos and understanding things. Till now, we did the phenomena of reflection. We studied reflection in spherical mirrors, plane mirrors. We also studied the phenomena of refraction, right? Now, what is refraction? Refraction is basically bending of light when light travels from one transparent medium to another transparent medium, right? So now, based on the concept of refraction, we are going to study lenses. Okay, what are lenses? Lenses are basically transparent spherical surfaces, right? There are different types of lenses. So how these lenses behave, how is the image formation in these lenses, right? As we studied in spherical mirrors, we studied two types of spherical mirrors, convex and concave. In the same way, we are going to study two types of spherical lenses, again convex and concave lenses, rules of image formation, how are our images formed, right? So let us see now. Okay, so what are lenses? Lenses are basically transparent spherical surfaces which are used to make light converge or diverge, right? We studied in spherical mirrors that a concave mirror is a converging mirror, it converges the light rays, and a convex mirror was a diverging mirror. In the same way, lenses are also spherical surfaces, transparent spherical surfaces, wherein they are used to either converge the light rays or diverge the light rays. Okay, that is either to concentrate the light rays to a point or spread it out. Okay, so in this chapter, we are going to study two main types of lenses. But before that, let's see what are the different types of lenses we have. Okay, so the different types of lenses, first one is a biconvex lens. A biconvex, we have studied what is convex. Convex is one which is tapering outwards. So this is called as your biconvex lens, which we are going to deal with in the entire chapter, right? The second type of lens is a plano-convex. Plano-convex has one side as plane and another side is convex. Convex means bulging out. Then we have a third type, that is convexo-concave, wherein one surface is convex and another surface is concave. So this surface is concave. Okay, so this type is a convexo-concave. The fourth one, this is called as a meniscus type, right? In the same way, we have plano-concave, wherein one surface is plane and the next surface is a concave surface. Then we have a biconcave, wherein both the spherical surfaces are concave, right? So in this chapter, we are going to study this biconvex and a biconcave lens, right? So let us first see how are these lenses made and what are the main terms, important terms related to lenses, because unless and until we don't understand that, we won't be able to understand the image formations, right? So first of all, we have studied in spherical mirrors that if we have a mirror is a part of a spherical surface, right? It will, because it is a part of a spherical surface, it will have a center, right? So if this is your spherical mirror, it is a part of a spherical surface, it will have a center of curvature. Center of the spherical mirror is called as a pole, right? The line joining center and the pole is called as principal axis. In the same way, we are going to study the same terms related to lenses. So for example, if I draw a convex lens, this is the convex lens, right? Now, this convex lens, the center of the convex lens, okay, is called as the optical center. Every lens will have a center. That center will be called as optical center. Center of a mirror was called as pole, but center of a lens is called as O, that is your optical center. Now we know as these are made of spherical surfaces, there are two. So in the next slide, I'll show you how convex and concave lenses are made. So right now, just keep it in mind, at both the surfaces are made up of spherical surfaces. Both being part of spheres, there will be centers of curvature and there will be two centers of curvature. So if this one is a part of this surface, this is going to be center of curvature 1 and there's going to be a center of curvature 2, right? So now a straight line which is joining these surfaces, okay, a straight line which is joining the center of curvature, optical center, both the center of curvatures, this line is called as the principal axis, okay? That's the principal axis. Now, obviously, if there are two centers of curvature, there are going to be two focuses. So this is your F1 and this will be your F2. So F1 is always called as a primary focus and F2 is always called as a secondary focus. So this is called as your primary focus and this one is a secondary focus, right? Centers of curvature, optical center, principal axis, principal focus F1 and F2. Obviously, there will be radius of curvature. What is radius of curvature? Distance between center of curvature and optical center will give you radius of curvature. Distance between principal focus and optical center will give you focal length. These two will be there. The formula governing these two, focal length and radius of curvature, will also remain same. We know that F is always equal to R by 2 or R is equal to 2 times F. This will also remain same. Okay. So as I had told you during spherical mirrors, if you understand spherical mirrors, lenses is going to be very easy, right? So if you can see in these diagrams over here, basically a convex lens, this is a convex lens. A convex lens is a converging lens. Okay. Now what are lenses? Now here, as compared to your concave mirrors, these were the incident light rays and they were reflected back, right? But on the contrary, what are lenses? Lenses are transparent mediums. So as they being transparent mediums, light will pass away from them. As you can see here, light will pass, they will bend. And we know whenever light travels from one medium to another medium, light bends, right? So as in case of a convex lens is always, as you can see, it is a converging lens. Converging, that means they will converge the light rays at a point. Now that point will be termed as focus. Understood? Here in this case, again, this is a concave lens. As both the parts are concave, it is a concave lens, and as you can see, the light rays are getting diverged. A concave lens is a diverging lens. Understood? So these are the parallel light rays getting diverged, but they appear to come from a point that is F1. So this is the point, first focal, principal focus. Understood? Now, all these light rays, can you see this? These are passing through optical center. Okay? Now let us see in detail. Now, if you can see, this is your convex lens. It is, how do you differentiate between a concave and a convex lens? A convex lens is tapering towards the ends. It is thin at the ends. Okay, so as you can see in the diagram, this is your convex lens. Okay, if you want to differentiate between a concave and a convex lens, so what is the convex lens? Convex lens is thin at the ends. This is also thin, right? This one is thin and it is bulging at the center. When you see, it is coming out, so it's bulging at the center. As I had told you earlier, a convex lens is part of two spherical surfaces, right? So if this is one spherical surface, the other one is another spherical surface. If I combine these two, right, if I take one part from this, another part from this, what I am going to get? I am going to get a biconvex lens, right? Biconvex lens. This spherical part is going to have this center of curvature. This spherical part is going to have another center of curvature. Center of curvature, we know this is going to be the optical center. And if you join these points, this is the length, or you can say aperture of the lens, right? Aperture of the lens. Again, this is going to be your focal length, f principal focus, f2. Understood how it's made, right? So if you see, what is a convex lens? A convex lens is a converging lens. Converging lens, that means, see, when you say parallel light rays coming from infinity, when rays parallel are coming from infinity, when they strike the center, this is the parallel light ray, it's coming from infinity. As it is striking at the center, it is going to pass through focus. They are getting converged at a point. That point is called as focus. All of them are getting converged at this point, right? So this point will be named as principal focus. And you know that this distance between principal focus and the center, that is this optical center, is your focal length, f. Okay, understood? Right. Moving ahead, we will study how your concave lens is made. Okay, so now if imagine these two spheres, okay, when these two spheres are just, when this spherical surface, okay, and this spherical surface of this another sphere, they are attached to each other, okay, like this, we get a concave lens. Okay, so as if you have to do a structure of a concave lens, what is a concave lens? Concave lens is bulging at the ends and thin at the center. Understood? This is your concave lens. Now again, in the same way, we know this is part of two spherical surfaces, so that there are going to be two centers of curvature. As there are two centers, this is the center of curvature, there is going to be two focuses, principal focus, f1, f2. And if you just join this center, this is going to be your O. That is your optical center. What is optical center? Optical center is the center of the lens. As already I've told you, convex lens is a converging lens. Concave lens is now going to be a diverging lens. It will diverge the light rays, right? It's going to be a diverging lens. It's going to diverge the light rays. So if you can see here, see, parallel rays from infinity are coming towards the center, and they are getting diverged in this amount. Parallel rays getting diverged. Parallel rays, okay, and anything which is passing through optical center will pass through, we have the same path. Understood? The green rays and the red rays, these are the parallel rays coming from infinity, getting diverged. Now when I take these light rays behind the mirror, okay, so when I take these light rays, for example, if I just extend them behind, I am extending them behind, this blue one, so they appear to come from a point behind the lens. Now that this point over here, this point is called as the principal focus. Understood? Now you'll say, ma'am, why light rays are always coming from this side, always from left side, right? By default in physics, as far as ray diagrams are concerned, we will consider that our object is always on the left, right? In reality, it can be on right. If it is on right, what will happen? Parallel rays will come from this side. They will get, they will pass through the lens, and they will get diverged in this way. That's not a problem at all. But just to maintain certain uniformity, right? Just to maintain some uniformity for ray diagrams and for our own, and we just to avoid confusions for our own simplicity, we take by default that the object is always going to be on the left. Understood? So in this way, your concave lens behaves as a diverging lens. Questions can come: explain how a convex lens is a converging lens, or explain how a concave lens is a diverging lens. Ray diagrams are very, very important in these cases. Both the ray diagrams should be practiced by heart, right? Okay, let's proceed now. Now, as we had studied rule formations for image formation, certain rules for image formation, we are also going to study rules for image formation of lenses. Two rules are same, the third one also being same, just the changes. See, the third one says, light ray passing through optical center will go away undeviated, right, without changing in direction. In mirrors, we studied a ray of light passing through center of curvature retraced the same path because it was reflection. Now this is refraction. It is going from one transparent medium to another transparent medium, right? So the third rule is changed over here, which says incident ray which is directed towards the center. Incident ray which is passing through the center of the lens, that is, it is passing through optical center, will pass undeviated. It will pass through the optical center. It passes without changing its direction. Okay. First and second rule will remain same. Incident light ray which is parallel to the principal axis will pass through the focus. Light ray which is passing through the focus will be parallel to principal axis. These two rules are going to be remain same. So parallel to principal axis, passing through principal focus, passing through principal focus, parallel to principal axis. These are the three rules based on which we are going to form our images from lenses, right? Okay, so now this is the experimental setup for image formation. Always, if you see this, they have taken a big table over here. Okay, so on this big table, we have kept a scale. Okay, the scale can be like 200 centimeters, 300 centimeters as the length you want. In between, we have kept this focus for, convex lens, because we are studying image formation by convex lens, right? So this is the convex lens over here. Now, this candle is our object. This candle is our object. Now, and the focal length of this lens should be known. Okay, if the focal length of the lens should be known, we can mark points over here. So this is the center where your lens is kept. If the focal length is, for example, 10 centimeters, so 10 centimeters from here, we will have our f1, and 10 centimeters from here, we will have our f2, right? And we know double is going to be our center of curvature. So another 10 centimeters from here, we will have C2. Another 10 centimeters from here, we will have C1. Now, many a times, C1 is also written as 2F1. That means 2 times F1, right? And C2 is also written as 2 times F2, right? That will not make a difference because we know that center of curvature, distance between optical center and the center of curvature is going to be radius, which is 2 times the focal length, right? So this will not make a difference at all. Now, over here, this is the screen. We know. Why do we use a screen? Because real images cannot be seen, right? Real images which are obtained, they are always and always obtained on a screen. Then only we are able to see it, and they are inverted. So if you observe over here, this object candle, right? We will get an image of this object candle on the screen and in an inverted format. That means it is a real image. Understood? So from here, just take an idea. In case of lenses, okay, in case of lenses, images which are formed on the other side of lens. This is same side of the lens. This is other side of the lens. Okay, images formed on other side of the lens, other side, are going to be real images. Okay, and images formed on the same side of the lens, that is here itself, if I'm getting an image, those images are going to be virtual images. Okay, we'll study this when we study image formations in detail. Understood? So this is basically your experimental setup. So what do we do here? We just keep on changing the position of our object, that is candle. For example, beyond 2f2, I'll keep my candle over here. Between, again here we are going to have 6 positions as we did in mirrors. First, infinity. Okay, second over there was beyond C. Now here C is taken as 2f2 2f1, so beyond 2f1. Third, we will have between this, so this position is this, between f1 and 2f1, f1 and 2f1. Fourth, right, this is beyond 2f1. Third is at C, that means at 2f1. Fourth will be between, at 2f1. Then we have between 2f1 and f1. Fifth, we have at focus, at f1. And sixth, we have between optical center and f1. So in the same way we are going to study, we are just going to move this object candle forward, and we are going to observe the images, moving the screen front and back. We are able to get the images on the screen. Understood? So let's see these image formations in detail in the coming slides. Okay, and as I've already told you, the positions for the image formations, right? Number one, what do we have? First is your at infinity. Second, beyond 2f1, that is center of curvature, C1. Third is at 2f1, that is at C1. Fourth is between f1 and 2f1, f1 and C1. Fifth is at focus. Sixth is between focus and optical center. So same way, again, if you know the positions for mirrors well, you are going, this is going to be very easy for you, right? So we know in mirrors also, when the object was at infinity, the image was formed at focus. Here also, now the object is at infinity, image is formed at focus, but on the other side, because this being a transparent medium, this will just go like this, right? So this point becomes your focus. Okay, so let's see this 1-1 position in detail. Okay, so the first position says, now where is the object kept? What is the position of the object? Position of the object is at infinity. Okay, can you see this parallel light rays coming from infinity? Yes. Now this is the convex lens. Convex lens is a converging lens. Where is the image position? Image is formed at f2. Image is formed at f2. What is the nature of image? I had told you, as the image is formed on the other side of the lens, nature always on the other side. In case of lenses, real images are formed. So nature of the image will be real and inverted. And size, as you can see, all the light rays are getting converged at one point. So size is highly diminished. Highly diminished. So this is your lens. This is the principal axis, optical center, f1 to f1, f2 to f2. So these are the basic things that you need to draw while drawing a ray diagram. So parallel rays, 1, 2. They are getting converged. Let them get converged at one point, right? So now this point becomes your principal focus. This is where your image is formed. Clear? Right. This was your first image formation. Let's do second image formation. Okay. So now in the second one, if you can see, now we are moving ahead. Okay. So now initially the object was at infinity. Now where's the object? The object is beyond 2f1. Right? It is beyond 2f1. Where is the image formed? Image is formed between f2 and 2f2. Between f2 and 2f2. This is going in the same manner as your mirrors were going. Okay, object image. Now what is the nature of image that you can tell? As the image is inverted and it is formed on the other side of the lens, nature is real and inverted. And what about the size? Object AB is this much, but image A dash B dash is a little smaller, so you can say size is diminished. Understood? Okay, so I'll show you how to make it. Lens, principal axis. First of all, draw a lens, draw a straight line, that is principal axis, and just put in all the main things that we have. F1, F2, 2F1, 2F2, right? This is your object AB. Take one ray parallel to principal axis, passing through focus, right? Take another ray passing through optical center. Okay, if it is passing through optical center, it will pass undeviated. So now this is your object where the two rays meet. This red one is your A dash B dash object. Okay, object is real and inverted, on the other side diminished, smaller than the object image, right? Understood? Okay, let us move ahead. Now we come to our third position. What is the third position? Third position will be as the object is at 2f1. So that means this is at C position, right? At 2f1. Where is the image formed? Image is also at 2f2, right? This is AB, this is A dash B dash at 2f2. Nature, again, it is going to be real and inverted. Real and inverted. What about the size? Size will be same, right? Size will be same. So now I'll show you how to draw this. Principal axis, optical center, f1, f2, 2f1, 2f2, right? Okay, this is my object at 2f1. Okay, now this green colors are my rays. Again, one ray, take parallel to principal axis, let it pass through focus. Another ray, let it pass through, just extend this a bit, pass through focus. Another ray passing through optical center. Yes, right? So now this is your, see, the red one is your image. So if this is A, B, this is going to be A dash, B dash. Arrows are very important. It will show whether it's inverted, right? Arrows, if your object, if you know that my object is standing like this, your image, if it is a real image, it should be standing like this, right? Because it shows the inversion. In real images are always inverted. Okay, keep that in mind. Understood the third one? Now let's proceed again. Fourth, what will come after 2f2? It will be between f1 and 2f1, right? So where is the object now? Object is between f1 and 2f1. Image, as you can see, as object is moving towards the lens, image is moving away from the lens, right? So image is beyond 2f2. Okay, nature, real and inverted. And what is the size? Size is now magnified. right? Size is magnified. So let us try to draw this lens, principal axis, f1 to f1, f2 to f2, right? So I'll keep my object AB between f1 and 2f1. Take one ray, again parallel to principal axis, passing through focus, another ray passing through, this is the optical center, so we have to take it passing through optical center, right? Take this another ray from here, passing through principal focus. I need to extend the yellow ray, extended yellow ray, green ray, they are meeting over here. But that's so this is the point where my object image will be formed. Understood? How is the image? The image is enlarged, that is magnified. You can also write over here enlarged, magnified. Okay, so if this is, always give object the name. Okay, if this is AB, this will be A dash, B dash. Give the name to your lens as well, MN, this being the aperture. Understood? Okay. Let us do the fifth position. Now, what will be the fifth position? Can anyone tell me? Okay, fifth position is going to be focus now. How did we go? We started from infinity beyond f2 f1, third at 2 f1, fourth between f1 and 2 f1. Now we have fifth. The fifth one will be at f1. This is the fifth one. Now what is my object? My object is kept at f1, right? Where will be the image formed? The image will be formed, we know, whenever anything is at focus, the rays coming out according to the rule, it will be parallel to principal axis. So all these rays will go parallelly, okay? And what will happen? Okay, the image will be formed at infinity, right? Nature of image, what will be the nature of image? Nature is going to be again real and inverted, as the image is formed on the other side of the lens. And size, as the image is formed at infinity, size is going to be highly enlarged. Highly enlarged. Let's try to draw this, right? MN, optical center, F1 to F1, F2 to F2. Always remember, this distance that you have taken should be equal to this distance. Okay, so my 2F1 should be here. Okay, so now I'll take my object. So let this orange one be the object. Take one ray parallel to principal axis, passing through focus. Take another ray which is passing through optical center. So if you see, how are these rays? These rays are parallel to each other. And where does parallel rays goes? Parallel ray always go to infinity. So that means the image is formed at infinity. Image formed at infinity are always highly enlarged. Right? Understood? Basically, ray diagrams for lenses are quite easy. Okay, so now next, what will be the next position? Next position is going to be between optical center and focus. Okay, this is my sixth image. Where is my object kept? My object is now between optical center and F1. So now we know, in the case of mirrors as well, now in case of mirror, concave was my converging mirror. So there also the sixth position, which was between pole and focus, a virtual image was formed. In this case also, when the object is kept between optical center and the focus, the first primary focus, image that we are going to get is going to be a virtual image, right? So that means it will be beyond 2f2, 2f1 on the same side. Okay. Now nature, as the image is formed on the same side, nature is going to be virtual. It's going to be a virtual and erect image. Okay. And size is going to be enlarged. There also, in case of a concave mirror, we formed an enlarged image. Here also, an enlarged virtual image is only formed with the help of a convex mirror, right? So now let us try to draw this. Convex lens, principal axis, optical center, aperture of the lens. Oh, this is f1, 2f1, f2, 2f2. Always you have to take the same two rays. First of all, let's take our object. This AB is going to be my object. Okay, this is my object. Take one ray parallel to principal axis, passing through focus. Take another ray passing through focus, passing through optical center. So now if you observe these two rays are not parallel to each other, right? They are not parallel. So if they are not parallel, that means they are never going to intersect. So will it happen that no image will be formed? Because unless and until light rays don't intersect, image is not formed, right? So this won't happen. What we do, we extend the rays behind. Okay, so this ray I will extend it behind. Okay, and the other ray also I'm extending it behind, right? So now here your rays are meeting, so my image is going to be this, right? This orange one is going to be my image. So if this is my AB, this is going to be A dash, B dash. Now as image is on the same side, it is going to be a virtual image. Understand? Whatever images are formed on the other side are always real images. Okay, understood? Very simple. And always remember two things. Take only two rays, one ray always parallel to principal axis passing through focus, another ray passing through optical center. It will pass. So somewhat the other way, it has to intersect. Only in the last case it will not intersect. So when you take these rays behind, they are going to intersect and a virtual image is going to be formed, right? So this is the way we have image formation by a convex lens, right? Now next what we are going to study is image formation by a concave lens. So just to revise, image formation by a convex lens, these are the six positions beyond at 2f2, 4, 5 and 6. As the same way it will work in mirrors. As the object is moving towards the lens, the image is moving away from the lens. Size is increasing. Size has an increasing trend in this manner. Highly diminished, diminished, same size, enlarged, highly enlarged. In this is a virtual image. So for the first 5 images, first 5 positions, we have real inverted, and only the last one is going to give you an enlarged virtual and erect image. That is when your object is between optical center and the first focus. First focus is always called as the primary focus. Okay, the second focus f2 will be called as a secondary focus, right? Okay, now let us study image formation by a concave lens. Here also we are going to have only two types of figures, right? So first position is going to be your infinity. This is the position 1. We know images objects which are at infinity, they are going to give us parallel light rays. So these are the parallel light rays that we have. Parallel light rays. And which type of a lens is the concave lens? Concave lens is going to be a diverging lens. So from here We are going to diverge the light rays. So as the light rays are diverging, they appear to come from a point behind the lens, right? So when I just take these light rays behind, they are appearing to come from this point. That point is your focus, okay, F1. So this is the way first image is formed. For point size image is formed in case of a concave mirror, and always in case of concave mirror we are going to get a virtual and erect image, as was the case in convex mirror. In the same way your concave lens is going to behave, right? Okay, so this is your concave lens. Where is the image formed? The image is formed on the same side. We know when it is in case of lenses, when it is on the same side, it's going to be a virtual and erect image, and it is point sized, highly diminished, right? Second position, anywhere between your optical center and this 2f1, center of curvature. Now again, take one ray which is parallel to principal axis. It is going to get diverged, but it appears to come from a point that is your focus. Take another ray which is passing through optical center. It will go undeviated. Obviously, the point where these things meet is going to be my object point, right? So this is the point where they are meeting. So this A dash B dash is my object. Again, as the object is on the same side, it is going to be a virtual and erect image. How is the size? Size will be diminished. It will be anywhere between focus and optical center. Okay, so these are the only two types of images that we have in case of a concave lens. Kindly practice your ray diagrams as far as possible, because whenever question comes, even if the diagram is not asked, make sure that you draw a little small diagram, so to show that your concept clarity on the subject is good. Okay, it will give a good presentation, right? Now, as far as the new Cartesian sign convention is concerned, we studied this in mirrors as well. It is the same in lenses as well. Okay, same will be there in lenses. So in lenses, we know, I'll take the scenario of a convex lens. Both of them, it's going to be same. Okay, this is your convex lens, right? So now let us draw a principal axis. This is going to be my principal axis. Okay. This is my optical center. F1, 2f1, f2, 2f2. This is the basic thing. Okay, this, I mean, before drawing any ray diagram, you have to draw this, and then you put your positions of the object. Again, as we know, according to sign convention, it will follow the same convention which was followed by your your mirrors. We have x-axis, y-axis. Okay, so this will act as origin. Your optical center is going to act as origin. Okay, so this is your x-axis, this is your y-axis, x dash, y dash. So this part is always going to be positive. This part is always going to be negative. So we know that as the object is always kept on the left side, your object distance u is always going to be negative, right? Now image will be formed on this side, on the other side. So v stands for image. Now if the image is a real image, okay, if it is a real image, it is going to be positive. If it's a virtual image, it is going to be negative. See, same thing is followed, just everything is opposite in case of lenses as compared to mirrors, right? So u and v are done. Which are the next two things? We have height, h at and h dash. So object stands like this, we know. Sorry. On the positive y-axis, this will be positive, and this is going to be negative. So as the object h, so you can say object size is always going to be positive because it's erect. H dash image size, or H1, H2 is the image size in some textbooks. H dash is going to be negative if it's a real image, positive if it's a virtual image. Okay, same sign convention is going to be followed. So again, with the help of the diagrams, let us see this. Positive, negative, up and down. This is negative, this is going to be positive, right? So this is same for convex lens, for concave lens, Cartesian sign convention is going to be same, right? Let's proceed now. Now we have the lenses formula and magnification. Okay, as we had the mirror formula, what was mirror formula? Mirror formula gave us the relationship between U, V, and F. What is U? U is object distance, V is image distance, and F is focal length. Similarly, in case of lenses also, we have the same thing. We have object distance, image distance, and we have the focal length of lens, right? So lens formula again gives us a relationship between all these three. Now, as far as the lens here, the lens formula is concerned, we have 1 upon V minus 1 upon U is equal to 1 upon F. What was there in mirrors? It was 1 upon U plus 1 upon plus was the sign. Okay, here negative is the sign. That's the difference. So always remember, lenses it's negative, mirrors it's positive. Lens formula. Okay, 1 upon V minus 1 upon U is equal to 1 upon F. Very, very important. Based on this only, you're going to solve your numericals, right? Again, what is M? M is your magnification. What is magnification? It gives us an idea how much your image is increased or decreased. So it will be again image height, height of the image upon height of the object, upon height of object. This is going to be same. Either it, in some textbook it is going to be H dash upon H, or it will be H1 upon H2 upon H1. Okay, H2 is image height and H1 is object height. Okay, now there's again one more formula which gives us relationship between all the four. Okay, V, U, V, H, and H dash. That is object height, object distance, image distance. All these three, and magnification as well. So very, very important. Again, M is equal to, right? M is equal to V upon U equal to H dash upon H, or M is equal to V upon U H2 upon H1. Same thing, right? This is very important. In case of mirrors, what was the formula? In case of mirrors, okay, I'm just writing mirrors so that you don't get confused. In case of mirrors, the formula was M was equal to H dash upon H, which was equal to minus V by U, right? In case of mirrors, it was minus V by U, but here it is positive. Okay, in mirrors, there was positive sign in the mirror formula, there was negative sign over here. In case of lenses, there's negative sign in the lens formula, here it is positive. Okay, very, very important to remember, because these small mistakes can cost you a lot of marks. Okay, so again, I will repeat: magnification H dash upon H equal to V upon U. Very important. Lens formula 1 upon V minus 1 upon U equal to 1 upon F. Okay, keep this in mind. Right, so next we have, in the next coming up episode, I am going to solve many numericals based on the lens formula, right? So stay tuned for that and revise all the formulas, revise all the concept, because sometimes along with the numerical, they also tell you to draw the ray diagram according to the situation given, right? So practice your ray diagrams thoroughly. Okay then, see you soon. Bye-bye.